you should tell us, Sarah, how we should run the meeting in general. So I thought that we should keep this as a workshop, so a lot of interaction. But I wanted to give a set of brief remarks to set the stage. We think we have a lot of friends from Stuttgart, from Poznan, you said. And wanted to tell you a little bit about how I think about this issue, because I think that will be a central issue. I've attended to, as a background, our group has been doing a lot of work on using HPC in global system science applications. I've also attended now multiple meetings in the US on the Exascale initiative that the DOE started a few years back. And there's an interesting report. All of you can take a look at it. And also the national, I was just looking at it, but the National Strategic Computing Initiative, NSCI, is also worth looking at. I think it's a little broader than exascale computing, but I think absolutely applies to it. So I'll take maybe 3 to 4 minutes to set the stage up, and then it's a discussion for all of us. But I wanted to cover the following points. First, I wanted to discuss, and they are not in any particular order, unfortunately, but I think that's okay. I wanted to distinguish between three kinds of computing that I think exists. One is compute-intensive systems. All of us know about it. We have also heard of data-intensive systems, and this is not uncommon anymore. A term that we coined back in our lab, which I have not seen used anywhere, is the notion of network-intensive computing. And I mean it in a very specific way and distinguish it between the first two ones. I don't want to define the first two ones, it's there. But it's really this interaction between either two processors or cores, or interaction between a memory unit and a compute unit at a particular rate that decides that this is a network-intensive system. And it's different than a purely data-intensive system because you're not moving large amounts of data in one go. It's really in small pulses that things are going through. And many of the simulations for, say, the pandemics have this kind of property. You don't do a large amount of data move, but you are sort of moving them in small pulses effectively. So that's one part of the story, and I think we should keep that dimension in mind as we discuss. The second dimension we want to keep in mind is the class of applications. So of course, this is about global system science, and at least as I understand, and we can discuss this, much of the computing in the first 30, 40 years was driven by physical systems, astrophysics, fluid mechanics, molecular dynamics, and they continue to be important applications. I think last 30 years, we have started seeing biological applications playing a big role and social applications playing a big role, especially with now Facebook and Google, and they have introduced new paradigms of computing as well as a result. And I think it's not just the applications, but the models that are used to work on these applications. So you might have a social application, but might end up doing a regression analysis. Then it's not very different than doing a regression analysis maybe in a physical system. So I think not only are the applications important, but the way the mathematics that is used to solve the particular class of problems within the application is important. So that's a second dimension. The third dimension is the access to the resources. Especially, we have folks from the supercomputing centers, but of course the commercial side is pushing very hard on clouds. I still think that clouds are not suitable for serious level of HPC. That's my view. I mean, we can argue. I've worked with Pete Beckman at Argonne. We tried to build a parallel cloud. It's not a straightforward issue to provide that many resources, but maybe for a certain part of the application, clouds work out fine. I'm not saying that they're not useful. They are commercially very viable, so we should not forget it. But that's one side. But that's not the only access model, and we should think about it. There were a couple of big push in US. The Exceed model is there. There's another model where you can do like SETI at home style thing where you have small amounts of information, but now they've all merged into this amorphous term called cloud. It's a term that exists now. The fourth dimension, I think, is the notion of computing where I think even the notion of HPC has to be taken into account. And I'm calling this computing on the edge. A term people have used before, but the idea is that we do not have computing that is happening in a single place, and especially for global system science problems, this is important. So through the IoT devices, autonomous systems, you have a lot of computing that's going on, essentially distributed out in the world itself. We carry our cell phones. This is actually a part of the computing machinery as well. So we're already doing computing on the edge, and this is going to grow even more. We expect the number of IoT devices to exceed 5 billion units in shorter. Maybe they've already exceeded. It's very hard to count what an IoT device. If you use phones as an IoT device, then it is we have crossed the number, and we are certainly going to cross it, right? So something to remember. So computing and sensing at the edge of the cloud, if you want to call it, is again a paradigm that fits into HPC, because that's how, especially for global system science problem, which is the focus, we need to keep this in mind. In a purely physical system, if you're doing molecular dynamics, we don't have to worry about it. But if you are studying something about social systems, this is an important part. So what I would like to at least put forward is a question for all of us to answer. What sort of HPC is needed for global system science? That's a fundamental question. And I think you need a particular class of HPC systems for doing analytics, machine learning, simulations. You need a different class of HPC systems based on this discussion for decision making. And you need a different class of HPC systems for information acquisition, sensing, and situation assessment. They are different class of HPC systems. So when we talk about, Alessandro talked about a particular class of HPC systems yesterday in terms of running simulations and Monte Carlo methods. That's one. But think about delivering HPC-based tools to decision makers who are on the ground, say in Puerto Rico right now, or wherever hurricanes happen in US, or earthquakes that happen in different places. They're also going to be users of HPC effectively if this is going to become a real-world thing. So maybe I stop here. Hopefully it gives you a sense for the range of things that I think we should discuss, because I don't think so we have a clear answer, but I think it fits with your bigger goal, at least the way you started the meeting. Yeah? Okay.
Thank you, Madhav. First comments to this from the audience. There's Eva. Just wait 1 second till you have the mic.
I have 2 questions. You mentioned the paradigm shift for the applications for social things, and I would like to know something more about this new paradigm, what you see there. And the second question is the accuracy of the computing if you go to one level higher from usual HPC to exascale. So the second is the accuracy. So if you imagine that you have algorithms that are iterative, and then you want to increase the number of steps to produce more meaningful results, or to get more parameters adjusted, then it is affected by the mistakes that are produced by the number of steps. So with each step you have some deviation from the real result for the rounding mode. So that is the second question.
Yes, so the uncertainty in the computing is an important question. So before I give an answer, I think this is a workshop and discussion, so others should feel free to jump in as well. It should not be one-directional part. So maybe you want to say, and then we can.
Yeah, you mentioned as the third point probably is the question of the access, since it has come over and over yesterday from the panels, from the interviews we have run. So the fact that this particular area of interest, which relates to social dynamics, let's say in a broad sense, of course, as you say, it requires kind of pervasiveness of the sensing. So it seems to point to a different architectural solution, so to bring computing as close as possible to the point of action. So how this can find a trade-off with the supercomputing in general and with HPC in particular, in view of the exascale challenge, because as you already said, probably going into the cloud, but I would say going into a distributed architecture might pose big challenges in terms of efficiency, effectiveness, and on the paradigm of the HPC in itself.
Right, that's why I use the term computing on the edge. That's the term people are using, and then I think Chris used the word fogs and mists, and we can have many other analogies to the environmental side. So maybe we can take 3 questions. So she had a question on the social, what's novel about social systems, uncertainty in when you do exascale computing, and then the access models. And I said I split the access into 2 parts. One is access or use of systems for decision making, and one for sensing and situation assessment. I split it purposely because the kinds of data movements you're likely to see in these 2 cases are slightly different. If you have sensors that are measuring temperature, for instance, or measuring the humidity, because it turns out it's an important portion of a sensing system for certain kinds of social science applications. For flu, in fact, it turns out it's an important thing to measure, right? So those things would be affected, as opposed to a decision maker taking an interest in a phone-like object with them, or computer essentially, to make decisions. So they want a very different amount of data and information that is being pushed to them down there, while small amounts of data pushed back into the system in the other case. So maybe first, my answer to the first one, and others should actually speak as well, is there are at least 3 or 4 different things that social systems present as challenges. And these are the only ones I have thought, but I'm sure others here have thought about it too, so please chime in, Chris and Rob. One is, network is a first-class object in this. In my opinion, without a network, social systems, that's the inherent aspect of it. It's a first-class object. You have, of course, when you do cellular automata-based computation of fluids or molecular dynamics, you impose a grid-like structure, but that's a convenience from a computational standpoint to do the numerical calculations. Here, network is inherent to the interactions. Secondly, the network is not regular at all. In fact, I think if this was like a grid, then we're back to the old world and we don't have to worry about it, right? And it's irregular in many, many different ways. And in fact, the open question is, how can we characterize a network like this? This has been ongoing discussion. Power law started to be the way we characterize. Everybody now agrees that that's just one parameter that quantifies it. Networks are much more complicated than just having a degree distribution, which is like a power law. But they have at least 4 or 5 different metrics people seem to agree to some extent, and this is not an exhaustive list, is certain aspects of degree distribution, certain amount of community that forms, certain amount of path lengths that are there, so they are well connected, or small world phenomena, certain amount of expansion, as it's called, cuts in these graphs, but those are all being enumerated. So every so often people say, okay, but this also seems to hold for social networks. It's a giant elephant, people are touching it and just adding new parameters. And this changes computing on these networks substantially, right? Because now, for instance, you can't do simple load balancing techniques that you're so used to, a geometric partition-based technique that people did doesn't work here. And we have, in our papers, we talk about this in a big way. The other thing is that the network, and my feeling is this is the hardest part, and I'd used this term yesterday, but I would like to repeat it, is the notion of coevolution. The network actually changes its structure in response to the dynamics on the network itself. And in some ways, the network so it's not static, it's not even dynamic in the form that the changes in the network a priori. There are forms of that kind too. But the real ones are where the network itself is adapting as the dynamics are going, right? This makes the problem much harder to do load balancing. So as an example, in pandemics, again, I use that because we talked about it yesterday. say on the 10th day, people might decide not to go to work because they perceive that the disease is moving rapidly. But what it does is it changes the social structure. It changes the network. Then some people might decide to vaccinate or take antivirals. Again, it changes the network. So effectively, you are having this interplay between a changing network and the dynamics. It's almost like water flowing through sand. It creates this network that goes around. So those are the things that are different, in my opinion. Uncertainty is an important question. I think it's going to become even bigger issue as we go to exascale. You rightly pointed out the amount of faults that you should expect in process when you have 1 million to 5 million processing units is high. I mean, there's a fault tolerance aspect there itself. So you did interval computing. You said there's probabilistic computing that is being talked about. Quantum effects are going to inherently introduce new kinds of error models. All this is open. I don't have a good answer of how we would solve it. It's case-by-case basis. And to your question, I completely agree. We need to have computing that is tailored for social systems. And this is the question I want to raise to this audience. Much of the development of computing, at least till recently, was based, at least for exascale, was based because of national labs asking the Intels and others, Dells and IBMs, to produce these machines for them. Very specific ones. They would have these contracts that run to a couple of years, and they'd produce a machine that can solve a problem that was physics-oriented. Maybe the Googles and the Facebooks and Twitters would drive the same way, but they have decided to take a commodity view. Apart from a couple of instances where neuromorphic computing is coming along, and Google has decided to just build it out itself. It doesn't even oftentimes go and Google seems to do everything itself. Once it feels a need, it just wants to build it itself. So neuromorphic computing is an example for neural networks that they have just built it out. So I'll stop here. I should not be the one who should talk. Others should chime in, I think, in this discussion.